In this video, we'll look at some of the VHDL constructs to get going with actually writing a simulatable and synthesizable VHDL model. The intent of this is to just give an overview of some of the capabilities of VHDL. There's a lot of capability that can't be covered and probably shouldn't be covered because it's information that is better left as something you look up. So the point of this is just to get you familiar with the general capabilities, and then as you need details on the syntax for a particular capability, you just know where to look it up. Okay, so let's begin with the anatomy of a VHDL file. So let's say that I have a system, and it's going to have an output F, and its inputs are A, B, and C. And let's say that we give this thing a name, system, let's call it X. And we want to create a VHDL model for that. So what we're going to do is we are going to have one file for each system. And the suffix for a VHDL file is .vhd. So what you want to do is you want to name the file in a descriptive manner. So you typically use the name of the actual system you're modeling. So for this example, I would do, okay, I'm going to call it system x.vhd. And within a VHDL file, you're going to have three primary items, okay? So the first one is going to be what's called the entity. And in the entity, this is where you describe all the inputs and the outputs. So this is basically the I/O. So we would describe that it had three inputs called A, B, and C, and it had an output called F. Then you're going to have another section which is going to be called the architecture. And the architecture is where you describe the behavior. So you separate out the I/O, the input and the output, or the ports of the system from the actual behavior in VHDL, and so you have two sections, the entity and the architecture. The other third one that you have in a file, and this is optional, is basically, I write it up here because you always do it at the beginning of the file, but this is going to be your libraries, and also called your packages. And so this is going to be additional capability that you want to include. So if you think about the VHDL, so it has a standard, so the IEEE 1176 whatever year standard, it describes all the functionality within VHDL in the base package. So that's actually called the standard package. We'll actually put it right here. So the standard package is all of the built-in capability that's in the original specification, or the most latest specification. If you wanted to add anything onto that, you would want to include another package or another library onto that. So for example, you can add things onto here which will give you additional functions or additional data types and stuff like that. And that's a topic for later. But the keyword standard refers to the library or the package that contains all of the information in the base package of VHDL. You don't need to put the standard library or package call within the VHDL file because it's implied, but you can put it there if you'd like to, just for consistency. Okay? All right, so within VHDL, one of the key things is that there are data types, okay? And every port and every signal needs to have a data type. So, for example, A, B, and C, and F, they're ports into our system. They have to have a data type associated with them. And so there's a bunch of built-in data types, and the data type defines what are the values that these signals or ports can take on, and it also dictates whether these are going to be synthesizable or not. So let's take a look at the first category of data types, and this is what's called an enumerated data type. So enumerated. So what enumerated means is that it's a data type where each and every value is explicitly listed out. Okay? So there's three main enumerated types. One of them is going to be called bit, and bit can take on the values 0 and 1. And as you might guess, this is the most synthesizable data type within VHDL. It is specifically there to model digital logic, so it is absolutely synthesizable. There's another type called Boolean, and Boolean is different from bit in that it takes on the values true and false. And so you don't use Boolean to model actually signals taking on a logic high or logic low. You use this for conditional checking. So you might say it's like if A is equal to 1, then the output is equal to 1. So these are used for checking, and these are synthesizable also. And then you have another type which is called character, and it can take on a large number of ASCII characters. So this is going to be like capital A, lowercase a, capital B, lowercase c. So basically anything that's in the ISO 8859-1 standard, which describes all of the symbols in the American, actually beyond that, it's the 250 ASCII characters. So that's what character is. So these are 3 data types. So when you defined a signal, it could take on bit, Boolean, or character. Now character, if it's not defined very clearly, it's not synthesizable. Okay, so then there's another group of data types which are called range types. And a range type, what this is it's a data type that has too many values to list out each and every one of them. So what you do is you just represent a small range and the large range, or the minimum and the max, and then you have some increment between them. So for example, there's a data type which is called integer. And integer can take on values between -2, 147, 483, 648 up to positive 2, 147, 483, 647. Now you look at that number, that might look familiar, because what that is integer is a synthesizable data type, and it synthesizes into a 32-bit vector. So this is actually the range associated with 2 to the 31 up to 2 to the 31 minus 1. So this is actually the 2's complement range of an integer. So that's where that comes from. So notice that I specified the minimum and the maximum, and then every value within here incremented by 1, every whole number, is representable by the type integer. Then there's also one that is called real, and this is going to be your floating point. And this represents fractional numbers, which go from -1.7 e to the 38 up to positive 1.7 e to the 38. And these are unsynthesizable unless you are very careful. So you might have to include specific packages. In fact, this is unsynthesizable unless you include a package which will give you a more specific definition of the actual floating point format you're going to use. But those are range types. Okay, so let's take a look at a few other types that are very common. There's also this group of types called physical types. And a physical type is something that contains not only, it can contain a number, but it also can contain a unit. So the most popular one, the only one we'll look at, is time. And so you can define a signal as time, and then it can contain a number, and then it can also contain a unit. So the supported units are femtoseconds, picoseconds, nanoseconds, microseconds, milliseconds, then sec, S-E-C, min, M-I-N, and then hour. And they're all based on a femtosecond. So the femtosecond is defined as 10 to the negative 15, and then a picosecond is 1,000 femtoseconds. A nanosecond is 1,000 picoseconds, et cetera, et cetera. So that's how you can actually have time in here. Now time is obviously unsynthesizable. It's used for simulation. Okay, then another very popular one is a vector type, and a vector type is a set of scalars where you define the vector to have a bunch of scalars that are all the same type. So bit underscore vector is a data type, and it is a linear array of type bits. Okay, so if I had an 8-bit vector, I would have 8-bit scalars. Then you also have string in here, and a string is a vector of characters. So this is a vector of bits, and this is a vector of characters. Okay, then almost wrap this up here. You have another one which is called a user-defined enumerated type. And this is where you can define your own type. So this is where you can come in here and you use the keyword type, and then you give it a name, and you say is, and then you list the values that you want. So you could create a type that's called stoplight, and then you could say it can only take on the values red, green, or yellow. So you could define a port or a signal of the type, stoplight, and it could then be assigned values red, green, and yellow. Okay, so then one more type that we'll look at really quick is going to be a array type. And an array type gives you basically a vector of vectors, or a linear array of vectors. So basically this is where you have, this would be a vector of scalars in here, and you're going to have a row of them. So what you do there is you actually you use the syntax type, and then you give it the name you want, and then you say is array, and then of, and then you tell it what it is of, and this is usually a vector. Okay, so a lot of these, this is just the overview, so you need to look at examples of it, and so we'll do that as we go. Okay, so now let's take a look at the actual details and the actual syntax of doing things in VHDL. So let's start with the library and the packages. So the library and the packages, I'll just zoom it in on here so you can go a little bit quicker. What you're going to do is you are going to have a keyword library, and you're going to tell it what library to pull out of. Now the primary library that you have is IEEE, because all of these packages are defined within IEEE. And so you say, I want to include the library IEEE, and I want to use specific packages. So then you give it the library name, and then you go dot, and then you give it the package name. So that's like std logic 1164 is a package, and then you do a dot, and you can say all to include all the functions within there, all the capability, or you can actually include just specific functions or specific capability. So this is an example of declaring 3 separate packages beyond the standard package in VHDL. So these, again, they typically go at the beginning of the file within the VHDL file, and you don't include them if you're not going to use them. And in fact, some packages will conflict with each other, so that's a whole topic in itself of understanding what's in the packages and how you actually use it. Okay, so then we need to look at the next main thing in a VHDL file, and that is going to be the entity. So within an entity, kind of the best way to learn this is to look at an example. So here is an example of something called System 1, and let's say we had 3 inputs, which are X, Y, and Z, and an output F. Well, remember that they need to have types, so they need to have a data type, and let's say they're bits. So here's how we can do this. You're going to define the entity by saying keyword entity. Then you give it the name of the system, and then you do a keyword is. Then you do keyword port, and the port is the name of inputs and outputs to a system. So that's the keyword. Then what you do is for each port name, so for example X, what we're going to do is we're going to give 2 pieces of information. We're going to tell whether it's an input or an output, and that's called the mode. So this right here, this first field is going to be the mode. And then after that, we're going to give it the type. So in this situation, the modes can take on in, out, and buff, but we're just going to use in and out. So X is going to be an input, and it's of type bit. So let's just call it bit, since this should be a synthesizable system. So then we can do a semicolon, and the semicolon means that this declaration is basically done, and we're going to go to the next one. Notice that the ports are all listed within parentheses. So you have an open parenthesis right here, and you have a closing parenthesis down here. So then we'd have Y is in bit, Z is in bit, F is out in bit, and there's a colon in between the signal name and the mode and the type. Then you do keyword entity. You can also put the signal names that have the same mode and the same type on the same line, comma delimited. So this equivalent entity definition or declaration would be X, comma Y, comma Z, and you would then say mode in, type bit, and then F, since it's alone, it would just be out bit. Okay. Okay, so that's how you do an entity declaration. Let's look at how we use the type bit vector, and we'll do an example here where we're going to have a system which has a 32-bit input vector and a 32-bit out vector, and its type is bit vector. So the way we do this, let's say that this is called system 2. We're going to go entity, system 2 is, we're going to go port, just like before, but now we're going to have the input, which is bus in, it's an in, and now this is how you declare a bit vector. So you're going to give it the type bit vector, and then you need to tell it how large the bit vector is. So the way that we do that is you come out here and you give it the range of indexes with a keyword in between down to. So in this situation, the high index is going to be 31 and the low index is 0. And those are used to address individual bits within it. So this right here is a 32-bit bus, or a 32-bit vector. And I can then use the index later to specify certain bits. So for example, if I went here later, I could say bus in 15, and I would say that gets assigned something. This represents the 16th from the right bit. Okay, so that would be a scalar. So this right here is going to be a scalar. So that's how you define bit vectors, and then that's how you address the indexes. But the keyword here is down to. There's also an up to if you want, but for synthesizable circuitry, you almost always put the lower index on the right, the higher index on the left, and that mirrors kind of the positional numbering system. So this, you can think about it, it's position 0, and then this is the most significant bit, or the position 31. Okay, so that's an example of an entity declaration. And then we get to the architecture, and the architecture is really where all of the capability of VHDL comes together, and there's a lot of capability that can be included in the architecture. So we'll just talk about some very brief things, and then we'll do examples of specific modeling approaches in the next video. Okay, so within an architecture, you're going to do the following. You're going to start it by saying architecture, and I'll write this out to slow it down a little bit. You're going to say architecture, and then you're going to give the name of an architecture, and then you're going to say of, and then you're going to give it the associated entity. So remember that within the file, there's an entity declaration. Well, the architecture needs to be attached to that entity. And the reason that you have it separate and you attach it is because some VHDL tools will allow you to have a file that has multiple architectures in it, and then you can dynamically swap in and out a particular architecture depending on the different modes or just different test conditions. But for what we're going to do, we're always going to use the same one architecture associated with the entity in its file. So we're going to go keyword architecture, the name of the architecture, of, entity, and then you say is. Now, within the architecture, it's going to have behavioral descriptions of stuff. And at the end, you're going to end it by saying end architecture, semicolon. Now, in VHDL, the semicolon is going to be how you end something. So whether it's a signal assignment or a declaration, you always end it with a semicolon. So this is an example of end architecture, semicolon. A comment in VHDL is 2 dashes. So what I can do is I just put 2 dashes right there, and then this is going to be a comment, and this will be ignored by the compiler or the synthesizer and the tools. And so what we do within the architecture is there's two kind of sections. There's a begin statement, which then starts the functional behavior. Okay, so this is where you model behavior. And up here is where you do declarations. Now, a declaration is going to be things like if you need to create a signal, an internal signal, you would declare it there. If you wanted to do a constant, you do it here. Then when you actually do behavioral modeling, it goes down here in the begin statement. So up here what you can do is you can create constants, you can create signals, you can create components. I shouldn't say create. You're going to declare. Okay. You can declare components, and then this is also where you would do a user-defined type that you were going to use in your system. So this would be a user-defined type. Okay, and then down here, this is where you do behavioral descriptions. Now, the behavioral descriptions, this is where we go into depth, where all the magic of VHDL is. So this can be quite long, so we'll do that in a different section. Okay, but I do want to look at declaring things, because you'll declare signals quite frequently to use within your behavioral model. So let's come over here, and I'm just going to draw a line right here. Let's look at how you would do a signal declaration. Now, a signal is different, declaration. A signal is different from a port in that it's an internal wire. So for example, if you had a system like this, and you had 2 inputs coming in, you had or let's say 3 inputs, and then you had an output, these are ports. Okay, so these are your ports. But you might do something where you want to take these in, and you want to, let's say, AND it, and then you want to take that and come over here and do an OR, and then that's going to go to your output. Well, this right here is an internal signal, so you need to declare that. Now notice that a signal is not observed outside of this system, but it is something that needs to exist, and it's used for connectivity. So the way that you do this is you say keyword signal, and then you give it the name that you come up with. So whatever, internal, N1, N2, whatever name you want to come up with. And then all you really need is then a semicolon and the type. So I put this in this little greater than or equal signs, or less than and greater than sign, to indicate that this is a required characteristic of the signal. So I could say signal, let's say I wanted to declare that as N1 for node 1. I'd say signal N1, and then I'd do this, and I'd say of type bit, semicolon. So that's how you declare a signal. Okay. Constants can also be declared in a very similar way, and constants are pretty handy. So a constant can be declared by doing the following. You do keyword constant, and then you are going to give it the name, then you're going to do a semicolon, and then you give it the type, and then you do this symbol right here, which is the colon equals, and that's like saying it's going to be initialized to the value, and then semicolon. So an example of that would, if I wanted to create a constant which was pi, I would say constant, I'd say it's called pi, and I'm going to spell it like that because I can't use, I think pi is a keyword, and then I would say it's a real, and then I would do this, and it was 3.14. So that's how you declare a constant. Okay, then you can also declare what are called components, and components are very important because they are other VHDL files that you want to include in this particular VHDL file. So that becomes very important when you do what they call structural design. So if I came along and I said, I want to have a system that is going to be made up of a system and then another system, and I'm going to wire these together like this and this and this. These might be other VHDL systems. So this might be a VHDL file, and this might be a VHDL file, and then this is a VHDL file. Well, this is fine. You can absolutely do this. You can instantiate these lower level VHDL files, but the way you do it is these are considered a component within the higher level VHDL file. And the way that you do that is, remember, it's above the begin statement, and you simply do it like this. You simply say component, and that's the keyword, and then you give it the component name, and this is very important that you name it exactly what the file is. So if the simulator can't find the exact file name in your working directory, then it will give you a compiler, or it won't find this and won't give you the functionality. So you say component name, and then you do the exact port definition. So whatever the port definition was for this particular system, you do this exact same thing here. So it's a signal name, colon, mode type. Signal name, colon, mode type. And then when you're done, you say end component. and that is it. So now remember, these are declarations, so it's almost like if you're going to use this one, you need to declare it as a component so that the VHDL simulator, the VHDL tool, understands that you are indeed going to use this, and this is the name of it, and this is the port definition. And then once you're after the begin statement, then you can start what we call instantiating these. And we'll look at instantiations later, where you can drop down A 1 time, 2 times, or 1,000,000 times. Okay, so that's a brief overview of the constructs in VHDL. In the next video, we'll actually start looking at how you model behavior. And you would model behavior, just as a reminder, you have your architecture statement, then you have your begin statement, and then you have your end architecture statement. And what we have covered is the declarations up here. So you can declare constants, you can declare signals and components. And then down here is where you're going to do the behavior. So this is what we'll cover next, is the behavior. And this is where there's a lot of different options available to you.